Welcome back, everyone, to another deep dive.
Always a pleasure to be back.
Today, we're going to be looking at something pretty crucial in the cybersecurity world.
Yeah, definitely. We're diving into a paper titled Introducing Perturbability Score, PS, to enhance robustness against problem space evasion adversarial attacks on flow-based ML-NIDS.
A mouthful.
Yeah, it is, but it's tackling a really interesting problem.
Yeah, this whole idea of adversarial attacks on machine learning systems guarding our networks.
Right, it's like you've built this amazing security system with all this fancy AI.
Like a super smart guard dog.
Exactly. But then someone figures out how to distract the dog or trick it.
Give it a fake bone or something.
Yeah, and that's what these attackers are trying to do with these adversarial attacks.
So this paper specifically focuses on a type of attack called problem space attacks, right?
Yeah, that's the core of it.
And this is different from what they call feature space attacks.
Exactly. In feature space attacks, you're basically trying to directly mess with the data the ML model uses.
So like changing the pixels in an image to trick the model into seeing something that's not there.
Right, it's like rewriting the model's code in a way.
Okay, but problem space attacks are more about manipulating the actual network traffic itself before it even gets to the model.
Exactly. It's more like, if we stick with that guard dog analogy,
Instead of rewriting its training manual,
you're messing with the real world around it to trick it.
changing the send to the intruder or something.
Yeah, something like that.
That makes sense, and it sounds a lot more difficult to defend against.
It is, because you can't just focus on protecting the model itself.
You have to think about all the ways the real world can be manipulated.
Right, and that's where this idea of the perturbability score comes in.
Okay, so this is basically a way to measure how easy it is to manipulate different aspects of network traffic.
Precisely. Some features are easy to tweak without breaking anything important.
Like the length of a data packet.
Right, you could add some padding to it and it wouldn't really affect the actual communication.
But other features are like the engine of the car,
Mess with those and the whole thing falls apart.
like the destination IP address.
Exactly.
So this perturbability score helps us figure out which features are most vulnerable to these attacks.
Yeah, and then we can focus on using the features that are hard to manipulate when building our security systems.
Like building a fortress with the strongest materials.
Exactly. And not only that, but it's like we're also making the fortress unpredictable.
So the attackers can't figure out where the weak spots are.
They're constantly guessing, and that makes their job much harder.
This is all really interesting.
It's a whole new way of thinking about security.
So now that we've got a basic understanding of this problem space and perturbability score,
Let's rewind a bit.
let's see how all of this came about historically.
Let's go back to the early days of machine learning security.
When researchers first realized that these powerful models could be tricked,
Ah, yes. The discovery of adversarial examples.
these are like the fake bones we were talking about earlier, right? Inputs that are specifically designed to fool the model,
Exactly. And initially, a lot of the focus was on what we call feature space attacks.
where you're directly manipulating the data that the model sees.
Think of it like you have an image classifier that can tell the difference between cats and dogs.
Okay.
A feature space attack would be like subtly tweaking the pixel values in the image of a cat.
So that the model thinks it's looking at a dog.
Precisely. But the problem with these attacks is that they're not very realistic in practice.
Because attackers in the real world don't usually have direct access to the data the model is using.
Right. They have to work with the real world inputs.
Like the actual cat itself.
Exactly. And that's where problem space attacks come in.
Okay, so instead of changing the pixels in the image,
You put a dog mask on the cat.
or dye its fur a different color,
You're manipulating the real world to trick the model.
that's much more devious.
And much more realistic.
And it's what led to this whole shift in thinking about the properties of the features themselves.
The realization that some features are just harder to manipulate than others, no matter how skilled the attacker is.
And that's where the perturbability score comes into play.
It gives us a way to quantify that inherent robustness.
Fascinating stuff.
This is where our deep dive gets really interesting.
We're going to explore the implications of this new metric,
For network security.
and maybe even beyond. Okay, so we've talked about this shift from feature space to problem space attacks.
And how this perturbability score helps us find those strong features that are hard to mess with.
But what does this actually look like in practice? Can you give us some examples of these different types of features
Sure, let's take a look at some common network features.
and see where they fall on this perturbability scale?
Exactly. Some high PS features, some medium, some low.
Okay, so starting with the high PS ones,
The ones that attackers love to target.
the low-hanging fruit.
Yeah, one classic example is forward packet length.
Okay, so that's just how big a data packet is.
Right, and it's pretty easy for an attacker to just add some extra padding to the packet.
To make it bigger without actually changing the data being sent.
Exactly, and the user might not even notice this happening.
So it's a stealthy way to try and sneak past the defenses.
Right, so forward packet length would have a high PS score because it's easy to change without disrupting anything.
Makes sense. What else?
Another one is forward IAT.
Forward IAT.
Yeah, it stands for forward inter-arrival time.
Okay.
It's basically the time between two packets.
Like the rhythm of the data flow?
Yeah, you could think of it that way, and attackers could try to mess with this rhythm.
By either inserting delays or speeding things up.
Trying to disguise what's really going on.
So these high PS features are like the obvious pressure points in a system.
Yeah, the things that attackers are naturally drawn to.
But you mentioned earlier that even manipulating these simple features can have unintended consequences.
Ah, yes, the collateral damage feature.
Right, so it's not always a clean getaway for the attacker.
Not at all. Let's say they try to manipulate that forward packet lengths we talked about.
By adding padding.
Right, but that seemingly simple change could have a ripple effect.
It could change the timing of other packets.
The overall size of the data flow, even how packets are broken up and put back together.
So even if they succeed in changing their target feature,
They might accidentally change other features as well.
and those unintended changes could set off alarm bells.
Exactly. It's like trying to quietly open a door, but you accidentally knock over a vase in the process.
You might have gotten through the door, but you've also alerted everyone that something's wrong.
Perfect analogy.
So this collateral damage makes things even more complicated for the attackers.
It does, and it highlights how important it is to think about all these features together.
Not just in isolation.
The whole ecosystem of network traffic.
Okay, so we've covered high PS features.
What about the medium ones?
What makes them different?
These are the features that require a bit more finesse to manipulate.
A little more skill from the attacker.
Exactly. Like, think about the number of packets in a flow.
Okay.
Changing this might involve splitting one flow into multiple smaller ones or combining several flows into one.
So it's not just a simple tweak anymore.
Right. It requires a deeper understanding of how the network handles data.
A bit more surgical.
Another example might be the average packet length within a flow.
Okay.
To change this, you might have to strategically add padding to some packets while removing it from others.
To try and keep the average consistent.
Exactly. It's a balancing act.
So these medium PS features are more challenging for attackers.
Especially for those who aren't as experienced or don't have sophisticated tools.
They have to think a few steps ahead.
Plan their moves carefully.
Okay, so now for the heavy hitters.
The low PS features.
The ones that are practically impossible to change without breaking things.
These are the bedrock of our security fortress.
The features we really want to rely on.
One prime example is the destination IP address.
Right, that tells you where the data is going.
Exactly. And if you try to change that,
You're essentially redirecting the data to a different location.
which will most likely break the connection.
It's like trying to change the destination of a plane mid-flight.
Not a good idea.
What else?
Another one is the protocol used for communication.
Like HTTP or HTTPS.
Right. Trying to switch protocols in the middle of a conversation.
Would be like suddenly switching languages.
Yeah. The other side wouldn't understand what you're saying anymore.
So these low PS features are like the foundation of a building.
They're essential and can't be messed with easily.
And the perturbability score helps us find these strong points.
And prioritize them in our security designs.
Okay, so now we have a good grasp of how this score works.
And how it applies to different features.
But how do we actually use this knowledge to build better ML-NIDs? What are the practical steps?
That's a great question. Let's dive into some strategies.
Let's talk tactics.
One key approach is what we call PS-guided feature selection.
Okay, so instead of just using all the features we can get our hands on,
We carefully choose the ones with low PS scores.
the ones that are hard to manipulate.
Exactly. We want to give our ML models the strongest possible ingredients.
So it's not just about having a powerful model.
It's about feeding it the right data.
Makes sense. But how do we actually identify these low PS features in the real world?
Well, the paper provides a framework for calculating PS scores.
Yeah, based on those factors we discussed earlier.
Right, but applying this framework takes some expertise.
You need to understand network protocols, data structures, the specifics of the system you're protecting.
It's not a one-size-fits-all solution.
So it requires a bit of analysis and customization,
Definitely. And that's where collaboration is key.
bringing together security researchers, network engineers, data scientists.
Combining their knowledge to create the best defenses.
So it's a team effort.
Absolutely.
This whole idea of focusing on low PS features seems like it would really make life difficult for attackers,
It does, because they can't rely on those simple tricks anymore.
like padding packets or messing with timing,
They have to find new and more sophisticated ways to manipulate the traffic.
which requires more skill and understanding.
It raises the bar significantly.
And that might even deter some attackers altogether.
If they see that a system is well protected,
It might just move on to an easier target.
it's like putting a beware of dog sign on your house.
Might not stop the most determined intruder.
But it'll keep the casual ones away.
I like that analogy.
Sometimes just making a system look difficult to attack.
Can be enough to deter threats. This whole discussion about the perturbability score has been fascinating.
It's a whole new way of thinking about security.
And I'm curious about its broader implications.
Yeah.
Could this concept of PS be applied to other areas where machine learning is vulnerable?
That's a great question, and one that researchers are exploring.
Because this paper focuses on network security.
But the underlying principles could be relevant in other domains as well.
Like where?
Well, one area that comes to mind is computer vision.
Okay, like self-driving cars, using machine learning to see the world.
Exactly. A problem space attack in that context could involve manipulating the physical environment.
To trick the car's vision system.
Right, like putting stickers on a stop sign to make it look like a speed limit sign.
That's scary.
And we could use the concept of PS to figure out which features of a stop sign are most resistant to that kind of manipulation.
So maybe the shape of the sign is more robust than the color?
Or the placement of the text is harder to change without being obvious.
So we could design more robust computer vision systems?
By focusing on those hard-to-manipulate features.
This could be applied to so many things.
Natural language processing, sentiment analysis, spam filters.
It's like a whole new framework for thinking about AI security.
It's about understanding the inherent properties of the data.
And using that understanding to our advantage. I'm really excited to see where this research goes.
Me too. It has the potential to change the game completely.
Well, before we get too carried away with all the possibilities,
I know you always have some novel notions up your sleeve.
those out there but plausible research ideas,
What's got you thinking outside the box this time?
well, this whole discussion got me thinking.
About
What if we could apply this concept of perturbability to not just individual features, entire systems?
Whoa.
Like imagine a system perturbability score.
That could tell you how resistant a whole network is to manipulation.
We could look at things like redundancy, diversity, complexity.
It would be like a stress test for an organization.
But instead of looking for financial weaknesses,
Or looking for security weaknesses.
we could simulate attacks, see how the system responds.
And find the points of failure.
This could be applied to so many things.
Power grids, transportation systems, financial markets, even social networks.
It would be incredibly valuable for critical infrastructure,
Knowing where the vulnerabilities are.
so we can prioritize our defenses. Of course, developing such a system-level score would be a massive undertaking,
It would require expertise from so many different fields.
but the potential benefits are huge.
Imagine being able to assess the robustness of a whole nation's cyber infrastructure.
That would be game-changing. But hey, these are just novel notions.
Food for thought.
We're not saying we have all the answers.
But we hope these ideas spark some creative thinking.
About the future of AI security, thinking about the perturbability of whole systems,
Yeah.
it really highlights how interconnected everything is these days.
It is. It's like a giant web.
You touch one part, and the whole thing vibrates.
And that's why we need to think about security in a more holistic way.
I can't just focus on individual pieces
We have to understand how they all fit together.
and how a weakness in one area.
Can create a ripple effect.
This paper has really given us a lot to think about,
It has.
from the technical nitty-gritty.
To the big picture implications.
But as we wrap up our deep dive,
I want to hear your thoughts.
yeah, what are your key takeaways from all of this?
I think the biggest one for me is that security is a constant evolution.
It's a never-ending game,
Attackers are always coming up with new tricks.
and we have to stay ahead of them.
This perturbability score,
It's like a new weapon in our arsenal,
it helps us understand how those attacks might evolve.
so we can build better defenses. It's like a game of chess.
You have to anticipate your opponent's moves.
And plan your counter strategies,
And that requires understanding their motivations.
their goals, their limitations.
Where are they going to strike next?
It's a constant cat and mouse game.
With really high stakes.
The security of our data, our networks,
Even our physical safety.
all depends on our ability to outsmart these adversaries.
And that's why research like this is so important,
It gives us the tools we need.
to stay one step ahead.
This paper has really changed the way I think about security.
Me too.
It's not just about building walls
It's about understanding the very nature of the systems we're trying to protect.
and using that understanding to make them stronger,
It's a shift from being reactive,
to being proactive.
and that's really exciting.
As AI becomes more and more integrated into our lives,
Security has to be a top priority.
not an afterthought,
It has to be baked in from the beginning
and that requires collaboration.
between researchers, engineers, policymakers.
Even the public.
We all have a role to play.
Well, folks, this has been a fascinating deep dive
It has.
into the world of adversarial attacks.
And the Perturbability Score.
We hope you've learned something new.
And maybe even had some of your own novel notions sparked.
Remember, the field of AI security is constantly evolving,
So keep exploring, keep questioning,
and keep pushing the boundaries. Until next time, stay curious.
and stay secure.